Hello, good morning, everybody here in the room and online. Thank you very much for coming here to this new Severo Ochoa colloquium. Today, the speaker is Raúl Carballo Rubio. Raúl was here already several years ago at the IAA, making his PhD thesis under the supervision of Carlos Barceló, who's there. And of course, as all the theses here defended at the University of Granada. Since then, he has been a postdoctoral researcher in 4 institutions in different countries with a number of collaborators. He's very active and a very promising researcher in this field. He's an expert on black hole physics with a particular emphasis on the study of, I have to read it, microstructure and its possible imprints at macroscopic scales. And since 2021, he's participating in the international project called the New Generation Event Horizon Telescope that you are all, I'm sure, aware of. Specifically, he's member of the Fundamental Physics Science Working Group, and within this group, he is co-leading the topic of quantifying horizon physics. And he has published about 50 peer-reviewed papers on one chapter and of course, many other contributions in different ways. And he has an index of 22 coming from, not from ADS in this time, which we are all used to, but Inspire HEP for the field of research. Today, as you know, as you all know, he will give his colloquium on testing black hole structure with very long baseline interferometry. So connecting the theory of physics, of fundamental physics, with the observations we are all expecting to have with the New Generation Event Horizon Telescope. Thank you very much for having accepted our invitation, Raúl, and now the floor is yours.
Thank you very much for the very kind introduction and also for the opportunity of being here, giving this talk. So I'm going first of all to say that this is fine, so you can see the slides. If I can do that. Yeah, I'm not sure about it. Let's see. Yeah, now we're starting with the technical problems. Okay, so. Yeah, I don't know.
Stop sharing?
Yeah? No, I think.
Stop sharing?
So can you do that? Because I don't know. This is what happens. Yeah, so I was trying to do that. Okay. Yeah, now you can share. Okay, well, sorry about that. And so yeah, I'm going to be talking about black holes and the very long baseline interferometry. I encourage you to stop me at any point to ask any questions. So, someone told me after a talk that they have a very nice voice for a podcast to go to sleep. Kind of like. So it implies that if I'm talking for 50 minutes, you're going to fall asleep. So yeah, just interrupt me, ask any questions, and yeah, that would be more interesting. So this is the roadmap that we are going to follow. So I'm going to be talking. Well, the talk is divided into main parts. The first one, I'm going to be talking about what a black hole is, and I guess you have an idea of what a black hole is. Probably different people in this room will have different definitions of what this means. But I think that this is far from an issue that is settled, and that's what I'm going to be discussing for half of the talk, essentially. And then I'm going to talk about how to, once we know like what a black hole is and what are the uncertainties in this definition, I'm going to be talking about how to see or how to distinguish between different definitions using observational data. So I'm going to be starting talking about black holes in classical gravity. And this is what a black hole is in classical gravity. So this is going to be a short anatomy class of what a black hole is in classical general relativity. So what we have is, so this is a picture of what a black hole would look like. So we have an outer boundary, which is the outer horizon. And so the important thing, so the outer part of it will be important later. So for the moment, we just have a horizon, which is a one-way membrane, a one-way boundary. So essentially, we can cross this all inwards. We cannot cross it the other way around. That's what many times is taken as the defining characteristic of a black hole. And we also have a core that I'm going to be talking more about. So sometimes this is what when we are explaining what a black hole is to general public, this is what we say, that this sharp boundary that defines the black hole. I think actually, I think this can be misleading in some ways, and actually it's better to think about this as a cloud, because essentially what happens at the horizon is not that there is nothing happening outside the horizon, then everything happens there. There is a region between what we call the photon sphere and the outer horizon, where interesting things start to happen. Essentially, what happens is that at the photon sphere, photons are going to follow circular trajectories, closed orbits. And if we imagine that we are sitting here in these points, and we have like a torch that we are emitting light, then part of this light is going to start being trapped. It's going to fall into the black hole. Okay? And essentially, even if we are pointing in the outwards direction. And that starts to happen at the photon sphere, becomes more and more extreme until we hit the horizon. Right? So essentially, there is a cloud around this is what the black hole is. Right? All this structure are not just a sharp boundary. And also in general relativity, we know that there is a singular, so the core is also singular, so there is a problem there. And this provides motivation to analyze extensions of this notion in the theory, in theories that go beyond general relativity. So just to summarize, these are the defining characteristics of a black hole. So we have a surface where photons follow closed orbits. Okay? That's the photon sphere. And then there's a region between the photon sphere and the outer horizon where a fraction of photons that we emit when sitting there cannot escape to infinity. So they are trapped by the black. And then there's a surface where no photons can escape at all, photons at all. This is the horizon. And we also know that there is a singular core inside the black. Okay? So this is the structure of a black hole in general relativity. Again, let me stress that often all of this feature here is stressed, or it's used for the definition, and then we forget about the other ones. But it's important to keep them in mind, and why is that the case? So the blue features are essential to understand observations. So if we forget about them, then we can, it makes more difficult to make contact with observations or to understand what's the interplay between these definitions and extensions of it and observation. So it's important to keep these blue ones in mind for that, from that perspective, and I'll discuss more about this later. And also, the features which are marked in red are important as motivation to go beyond the theory of general relativity and consider extensions, in particular, to consider black holes in quantum. So that's why it's important to keep in mind the whole set of features. Yes?
And here's the first question. Thanks. I'm trying to make myself clear between the photon sphere and the horizon. So the photon sphere is it like an infinitely small layer where if I launch the photon into the right direction, it will be on a closed orbit, right?
Yes.
Okay, good.
Yeah, essentially the photon sphere, so you can think about it like you are trying to measure how many photons you lose if you are sitting in one point in space-time and you are emitting light. And then you calculate how many photons you lose to the black hole, essentially, because you have a black hole in your space-time. So at the photon sphere, you lose essentially one photon that is going to be, it's not that you lose it to the black hole, but you lose it to the gravitational field of the black hole, right? Not to the horizon, and then you lose only one. If you go a little bit inside, you're going to lose more and more until eventually you lose all of them where you are at the horizon. So that's does it make sense?
I mean, I will always lose some photon, right? I mean, if I point...
Yeah, of course. What I mean is that, so you lose some photons that you wouldn't expect if you were in flat space-time. Because they are pointing, of course, if you throw things at the black hole, you know that you're going to lose them. But if you throw them away from the black hole, essentially it's like kind of like imagine the black hole is behind me. So I don't expect any of these photons.
Away from the black hole, it stays in a circular orbit.
Yeah.
Not tangential, it's just away in the...
Yeah. Yes.
if I may ask, if I understand correctly, the boundary of the photon sphere, or the photon sphere itself, is the surface, the first surface where I can get close to it.
Yes, that's it. Yes, that's true. Yes. And when I'm thinking about away from the black, throwing things away from the black hole, the black hole is behind me, and then I expect if I emit rays this way, I don't expect any of this to go into the black hole. But as I get closer to the black hole, some of these light rays are going to bend, and they're going to go to the black hole. So I start losing them. Okay, so yeah, these are the features that we have for a classical black hole. And then I'm going to, as I said, so the fact that we have a singularity, we have a problem in the very definition, invites to consider extensions of this notion. So I'm going to be talking about then what black holes could be in quantum gravity. Okay, that's because we expect quantum gravity to be able to solve this problem of the singularity and give us something that is regular. And in the same way that the previous one was an atomic class, this is going to be a clairvoyance class, meaning that we are going to try to predict or to say what we expect quantum gravity to do, because I mean we have good indications that could be this way, but we don't really have a picture like this one, like in the classical case. So we expect that the picture we will have in quantum gravity is something like this, in which we have now a regular core. We are solving the problem of the singularity. The features are going, in principle, to stay the same. So we are still going to have a photon sphere. We are still going to have an outer horizon, in principle. The thing is that there is a price to pay, in general, in order to have a regular core, which is we also have an inner horizon. And that's why I was making the distinction between the outer horizon and the inner horizon before. So it implies that we have another element in this set of features. So we still have the blue features, again, this photon sphere and this region where we trap more and more light. We still have the outer horizon. We have a regular core, so now we solve the problem, or we expect that this problem is going to be solved. And we have a boundary now, which is an inner horizon. And the definitions of outer horizon and inner horizon are similar. So essentially, the outer horizon is an outer surface where no photons can escape from inside. And also the inner horizon is also an inner surface where no photons can escape also from inside. Essentially, we have two regions, two boundaries where that happens. Now, the problem with this, well, not a problem, but the observation or something that is it's important for the whole picture is that inner horizons are generally unstable. And this, so this kind of inner horizon is also, it's not that it appears only for this type of black holes in quantum gravity or extensions of general relativity, but we know them also in the framework of classical general relativity when we consider rotation or we consider charge. And we know in that framework that they are unstable. So they have some features, like essentially the way matter behaves around them makes them unstable. And this is also the case in the case of so we have strong evidence that this is the case. Okay. So then this implies that perhaps the structure is going to change a little bit, because if the inner horizon is unstable, then it may be that the system, in order to become stable, is going to get rid of this inner horizon. And the only way to do that is to also get rid of the outer horizon. Essentially, there is a possibility, again, this is just a theoretical possibility, that the system evolves in a way that we get rid of these two features. So they are not going to longer be there. We are still going to have a regular core, and we are going to have a surface that, again, a photon sphere, and this region where light behaves in that way. But we may be losing, actually, the defining feature that, as I said before, is like used or is sometimes the only one that is stressed in the case of classical black holes. So of course this opens the question, if we lose that feature, if we lose the horizon, right, the outer horizon, then what happens with observations? Are we going to, is this compatible with observations? Are we going to enter in a strong contradiction? It's like, we kind of like, is the theory perhaps it's not making sense? And the thing is, that's why it's important to keep in mind the blue features, because they are still going to be there in general. And as I said, these are essential and give enough freedom to us to maintain compatibility with observations. And that's why it was important to keep this in from the beginning. So just to kind of to provide a picture of what could be happening, again, this is something that is being it's the focus of active research. In particular, in this paper, which I reference here, the paper contains a calculation showing that semi-classical effects can give to this distribution. So we can imagine qualitatively that when we form in gravitational collapse a black hole of this sort, then initially it may have an inner and outer horizon, but dynamical effects are going to imply that the inner horizon is going to move in the outwards direction until it meets the outer horizon, which is also evolving dynamic. And they may disappear or leave something that is still, that doesn't have horizons, but that again still have the photon sphere, because the region is untouched and has a regular. Okay. And this is still unclear whether that's the complete picture that is going to be happening, theoretical, but it's a possibility. And again, it seems to be there seems to be evidence based on the instability of the universe. But so we need to keep in mind is that the structure of black holes beyond relativity is complex, complicated, and there are still many uncertainties. And ideally, we would like also to see if observations can allow us or can help us in order to be able to distinguish this structure. So with this motivation, I'm going to talk about black holes in astronomy, like not in general, but I think some particular aspects of this issue. Like in this slide, I don't have much to say because I'm going to be talking about this for the rest of the talk. And now this is more like a cooking class because we get some data and we need to be able to play with the data and to do something nice with the data in order to understand what's happening inside, right? Because now what we want to do is that, okay, we get some data and I want to know what the data is telling me or what's happening inside. Because again, I have also theoretical motivation telling me that there could be many things going on there and it's non-trivial. So I really want to know if the data can tell me what's going on there. And perhaps it can tell me something about the photon sphere, can tell me something about the region in which photons become increasingly more trapped, and we don't know if it's telling us something about horizons or things inside. So these are open questions, and I'm going to be talking about this for the rest of the talk. Again, this was just motivation, and to connect with the rest of the talk. So this was the first part about what black holes are. So if you have any questions about this, let me know before I move to the next part. And I give you a few seconds to think about this. And I'm going to drink some water in the meantime. Yeah, one question.
So, what are the timescales more or less of the meeting of the inner and outer horizon?
So that's a good question. So we don't know. We don't actually know. It depends on the theoretical models. There are theoretical models in which this happens slowly. There are models in which it happens more quickly. And the fact that why we don't know is because we don't have a good control of the dynamics of this evolution. So then we need that in order to understand the dynamics. So it's an open goal in theoretical research, which is essentially putting together all the ingredients that can have an effect on this dynamic, and then being able to solve these equations and see what happens after the
So, if I understand right, the horizon may completely disappear. So you have a photon sphere where photons get trapped, but then inside they can get out again. No. What does it mean that the horizon disappears? So in the photon sphere they get trapped on circular orbits, but once I go further inside, there's a possibility for them to escape again.
A fraction of them.
A fraction of them.
The deeper you go, essentially, the less fraction of them is going to escape.
Okay.
Essentially more.
It's like an asymptotic thing or okay.
I have a question about the instability of the inner horizon, because I understand that in this scenario, the very appearance of the inner horizon is an effect of quantum gravity integrations, which regularize the singularity. But then that means that the Einstein field equations will no longer hold; they are somehow changed. And the result of inner horizon instability is the result of general relativity. So in that sense, don't we also expect that the same quantum gravity effects, whatever they are, who created the inner horizon can also change its stability properties?
Yeah, that's a good question, and that can be like, the thing is that, so when I say instability, so I'm talking about an eternal situation, a situation that doesn't has a horizon for. But when thinking about dynamical situations, the instability can be seen as kind of like a sensitivity of the position of the inner horizon with respect to local energy content, energy matter content. Okay? And then that implies, of course, that's going to depend on the dynamics, but you can do some general arguments saying that if you have some matter that satisfies certain energy conditions, for instance, the inner horizon is going to move towards the interior, and that's what happens in classical general relativity. When we create it in gravitational collapse, it goes quickly to r equal to 0, right, to the origin, and then we have a singular. Right?
Yes, but that uses the Einstein-Field equation.
Yeah, that's what I mean. So, but if you violate energy conditions, then the inner horizon moves in the outer direction. And that's what you expect, like in quantum gravity, for instance, to have these contributions. So from that perspective, so the fact that you have modified equations doesn't invalidate the let's say that the statement that the position of the inner horizon is very delicate or very sensitive to having local energy and matter content there, and it's going to move in the outwards direction. And of course, like there's still you still need to have a good control of equations and being able to really show that that's the case. So some other question? No. Okay. Well, so I'm going to change a little bit, or to talk now about the problem. As I was saying, it's like we have theoretical motivation to analyze what we can say with data. And in particular, I'm going to be talking about the observations, VLBI observations, so a particular kind of observation that we can do. And for that, I'm going to be discussing first a phenomenological model. So we are going to kind of try to parameterize, because we have this theoretical uncertainty. So we could always take a particular theoretical model and then see which are the features that we see. But what I'm going to do here is to do a phenomenological model, which kind of allows us to parameterize all the possibilities. So this model is going to be constructed as follows. So instead of having a black hole, which we know again, so it's going to be to have this boundary and then the region around it, in which light has this behavior and has a boundary which you have pure absorptive boundary conditions. We're going to change this by an object that has a radius which is slightly larger than it. Okay. And it has a behavior which is different. So the boundary can behave in a different way. So instead of absorbing everything, remember that this boundary was absorbing everything in the case of black hole. Now we could have absorption, we could have reflection, some emission, some transmission, and we can have light that goes through it. And essentially, this is the most general thing that you can consider. And again, you can change the radius, right? So this is like just being very general, but you can consider this kind of like takes into account many theoretical possibilities. Again, like in terms of these coefficients, a black hole would have kappa equals to 1, it's a black hole. And you can imagine a wormhole, and then that will have different values of the coefficients. You can imagine a regular black hole. You can consider a horizonless star, again, a situation with no horizons, as I was discussing before. So this is essentially, a phenomenological model that can describe many different situations. And the question that you can ask now is, okay, I'm going to see what observations can tell me about these coefficients. So let's see if I can constrain them, or if I can say something about them. And then once I have this information about the coefficients, I can say, okay, perhaps if there is a strong constraint on a particular coefficient, I can conclude that a particular theoretical model in which this coefficient is high or has a particular value is not correct, right? Or it requires some changes. So, and I'm going to be working in spherical symmetry. So this is because this is what we were doing in this paper, and that it's referenced there. And of course, it's something that it's work in progress to generalize this to situations with rotation, which is necessary, right? In order to really compare with observation. So this is kind of like a first study of this issue in spherical symmetry. So now with this, so this is the central object, and in order to see, yes.
Why do you include emission in the summary?
Yeah.
Why do you include the emission factor in the summary?
Yes, because I'm thinking that there is no intrinsic emission. So I mean, it's that by emission I mean like I throw some energy into the object, and then the object emits part of this energy back to me. So it's kind of like energy conservation.
Why is it different than reflection? Is there like a time?
Yes. So there could be reflection, it's going to be instantaneous, right? It's also going to be, I mean, if it's like a mirror essentially, it's going to behave in a very particular way. If you throw a ray, you know that it's going to satisfy Snell's law, and then you're going to have certain properties. Well, emission can have like, generally it's going to be, you can model it in an isotropic way, you know, like essentially it's going to be absorbed, and after a certain time scale, it's going to be re-emitted in a way that is not related or correlated with the initial angle of incidence. I don't know if that explains.
Maybe in a different wavelength?
Yeah, certainly that can happen with different spectrum, yes. So this is something that you need to parameterize as well. So, this is how we parameterize the object, but we need something else in order to see what's, to image the object. Is an accretion disk. And in particular, I'm going to consider, again, a very simple model. And of course, one needs to consider more complicated models in order to be able to understand how astrophysical uncertainties affect what I'm going to say. But for the moment, we consider a geometrically thin, an optically thick accretion disk, and that's going to be surrounded in this object. And what we want to know is that if we have a camera there at some, with some angle with respect to this axis, and it's far away from the object, so we want to know how we see this accretion disk and how we see the central object, right? Essentially, because we know that we are going to get rays from the accretion disk, and we are going to get these rays, but then also some of the rays, they can go around the object and then can hit the camera, and this gives rise to photon rings, and there could be also some information coming from these boundary conditions. If there is reflection here, so we expect to see it. So in practice, how this works is that we do some ray tracing from the camera. Essentially, we start integrating rays from the camera to the object, and we follow them and see where they hit, and we apply the necessary boundary conditions, and we essentially solve some differential equations, and that tells us how to the image that we see with that camera of this object. So now this model can be used to test different things. And again, regardless of the theoretical motivation that you have, it's interesting in order to analyze and to understand the information that is encoded in the data. Because imagine we could do something simple, which is, okay, we don't have, these are many coefficients, I don't care about these coefficients, I just care about, I have something that has pure absorption, a boundary like that, like a black hole, but now I want to know my observations, how sensitive are to the radius. So essentially, if I change the radius of this, and that's kind of like modifying general relativity, because general relativity have a fixed value of the radius, right? If I change that, can I see that the observations? Imagine I have an object which is like 1 point something times the size. So that's something that you can ask. Essentially gives you an idea of how deep your observations can reach in this region that was between the photon sphere and the area, or on the surface of the object. Of course, we can also understand features which are associated with these coefficients, right? So essentially, you can use this model in different ways in order to understand what your data is telling you of these parameters. So questions about this before I move to the next slide or section? Okay. So yeah, that's the model we are going to be working with. And again, so the motivation is that we have some theoretical uncertainties that we want to parameterize. So now I'm going to focus in particular on a particular aspect. Okay, so it's like from this parameterization, and when you do this analysis, there are going to be different things that you can see in images. I'm going to be focusing on a particular one, which is two rings, and the reason is the following. So imagine now that from all these parameters, I take a very simple example, and I take this because it's kind of like simple to think about, which is I just consider reflection. I don't care about the other coefficients. I just have, essentially what I'm doing is I'm replacing a black hole with a mirror. So I have a spherical mirror, and I'm changing a black hole with a mirror. So that's what I do, okay? It's a big change, because a mirror doesn't behave like a black hole. So it's kind of like the opposite in a way, right? So what I'm asking is, okay, so how does this look like? So these are very theoretical exercise, because I'm doing something that, again, we don't expect quantum black holes to behave like mirrors, right? But it's kind of like just a very simple thing that I can do, like very abstract, and I want to see what I can learn from this. So in this case, what happens is that, for instance, you can see this, so these are the rays. This is what the ray tracing code is doing essentially. So I have the central object, which again, it's a mirror, so it's going to reflect rays like this one. If you have a ray doing this, it's going to be reflected. And this allocation disk that is emitting rays. And the different colors is essentially, it's just a code to keep track of where the rays are coming from initially and where they are, the part where they are reflected, okay? So it's not particularly important. So what is important for the purposes of this slide is that, imagine you have a photon like this, that is emitted this way, and then it hits the object here. So in the case of a black hole, it would be absorbed, it would disappear. This photon, we would never see it apart from the black hole, apart from the object, right? In this case, because it's reflected, we are going to eventually see it when we are far away, and that's going to give rise to the additional features in the images, in particular to additional rings, which are here. So in this image, so the two ones, this one is what happens when you put the camera here on the axis and look down, and this one has some inclination angle with respect to the axis. So essentially that's the difference between these two ones. So let's focus on this one here. Let's see if I have, if I do this, yeah. So this is the image of the accretion disk. This is what I see if I'm looking from the top, right? So I see the green photons coming straight to me, and the red photons. So these are the, again, imagine I'm looking from the top. And I also see the reflection in the mirror. So this is the reflection of the accretion disk on the mirror. So essentially that's what I see here. What I see in the middle, it's photons that go around the object and are also reflected. Okay? And I also see photons that can go around the object without being reflected. So it's essentially a combination. So so these are the ones, the photons that go around the object do like this without being reflected. We expect them to be there in general relativity. We know they are there, and that would give rise to photon rings, which are rings in the image, right? But then in this case, we have additional rings. So because we have reflection, we're going to have additional rings. And essentially, we have an additional ring structure that we wouldn't see in general relativity. Okay? So that's essentially what happens when you have a mirror. When you change a black hole with a mirror, you replace it with a mirror, you get the features that you see in general relativity, plus some additional rings, plus an inner reflection. That is, again, there was this one here. Huh? Yes, this one. So essentially, so that's something that you can aim for. I mean, if you have data, you can say, okay, let's see if I can see these additional rings, if I can place constraints on these additional rings, and that way I can place constraints on this reflection coefficient, okay? And rule out this model. Just for completeness, also say that these additional rings also appear if you have transmission. So essentially something similar happens if you allow photons to go through this structure, then you have something similar happen. Okay? So that's just for completeness. So the main idea is that it's interesting to look at additional rings, and I'm going to focus now, instead of having, I mean, as you can see, you have several rings, and in practice, if you were able to zoom into this image, you would see an infinite set of rings. Again, that happens also in GR. But we can consider the simplest model in which we have two rings. So instead of having just one ring, we have two rings, and we expect the second ring to be coming from reflection or some other process, transmission, and we want to see if we can see that in observations. Yeah? So we can. That's the problem we want to analyze. So then we can just do, again, we could take a particular model and analyze and use a particular model, or we can be as general as we want, as general as possible, and consider the problem of having two rings like this one. So what I'm proposing now is that I have an image in which, so like the image before, we had the accretion disk and we had additional rings, right? But I'm going to isolate these features. So I just want to analyze two rings, because I want to really focus on this to see if I can see the difference between one rings and two rings. And the other ones, I consider them to be subliving, essentially. So we can consider an image which is like this one, in which I have two rings, and I have an intensity profile which is very simple. So there is no intensity here. This would be the image plane. Then there's a step function here, so that I have points here which are bright. Then I have also no points with no brightness here, and I also have a step function here. Right? So these are essentially two perfect disks, or two perfect rings with a profile which is given by a step function. So that's the function here. So essentially this defines one of the rings, essentially like this one. This is going to be the diameter of the ring, this is the width. Yeah, so this gives you the one of the rings. So the total flux in my image plane is going to be a linear combination of the two of them. So I'm going to have one ring here with one diameter and one width, and a second ring with some width and some diameter. Okay? And that's what I'm proposing to see what this looks like, or if we can say, taking a look at the data about this kind of structure. And so again, these are geometric parameters. We have the diameter of the ring, we have the widths, we have the separation between them. And just for the sake of being precise, every time I have an image or some data or some plots in this talk, I'm going to be taking these particular parameters, which are the same ones in the paper that it's going to appear soon. So yes, I always fix specific parameters. So now, ideally, what I want to know is how can I see this in the data? So how does this look like? Because this is in the image plane, so this is very theoretical still, because even if there are like several jumps, like going from a theoretical model to now I'm considering a phenomenological model in the image plane with two rings, it's still very theoretical because observations don't give us data in this plane. So I don't get direct, the observation is not giving me the brightness of one of these pixels. It's giving me something, right? So I need to discuss that. The first thing that we're going to do, that's what I'm going to be discussing next, which is the observability of this two-ring model. So the first thing that we need to do is to consider the Fourier transform of this, because that was in the Fourier plane, in the intensity plane. So where we have this intensity, which is proportional to the flux that I was discussing before, and essentially it's these step functions giving me two rings. Okay. I'm going to do a Fourier transform of this image. There's going to be some observation wavelength here that depending on the observation wavelength. Essentially, that way I'm going to get a function that depends on two variables, which I will explain the meaning of it later in the next slide. So essentially, I'm going to get, it's just doing the Fourier transform of the function that I had before. And when you do that, in this case, in this very simple case, it's possible to do it analytically. That's why I was considering this particular profile with step functions. And the result is this one. So essentially, you get a sum. It's a linear problem. I have two functions for each of the rings. And the function of the two rings, they look the same. So essentially, you have a linear combination of Bessel functions of the first kind, the ones. And then I have the parameters, the outer radius of the ring number one, and the inner radius of the ring number one, and then the same, the outer radius of ring number two, and the inner radius of ring number two. Okay. And this essentially k is just the distance in this UV coordinates. So the important thing to keep in mind is that this is because of these are Bessel functions, so this is going to be something that is going to be oscillating. Okay? So this function here, it's just a linear combination of that, and if I plot it, it's going to be something that oscillates, goes from positive to negative values, and then it has a series of some zeros. Okay? So it's going to be vanishing at different points, and of course the points in which it vanishes, it's going to be depending on this parameter. Okay? If I change the parameters, I change the places where it vanishes. But essentially, I can numerically determine the places where it vanishes for a given set of parameters. So if I fix the model, I fix the rings, the radius of the ring number one and ring number two. And again, inner and outer there, it's the boundaries of the rings. Okay, so this is the inner boundary of the, so inner means, okay. Yeah, nice. So this inner means, this is the inner radius of the outer ring, and this is the outer radius. So these are the two parameters that I'm using. So that's not the only thing that I have to do. So as I was telling you, that I was going to explain what these EOB coordinates are. And so when I do an observation with a given array of telescopes, of radio telescopes, I'm going to have, so essentially what I'm getting from the information I'm getting from these telescopes is this function u of u and v evaluated on coordinates which are the difference between two stations. So now imagine I have an array of telescopes, and for idealized purposes I'm taking something that is very ideal, so it is not a real array that we have, in which I have a series of radio telescopes forming this, this square, and then what I'm getting, or the information I'm getting, is this v function evaluated. If I take two stations, I have this would be the u coordinate, and this would be the v coordinate, okay? And this is defined for each pair of stations. So once I have a pair of stations, I get this uij and vij, and that's the Fourier component that I'm exploring, or that I'm detecting using these stations. And then, like again, for the figures I'm going to show here, I'm just going to be using a particular value. So I'm going to use like a square array like this one, in which I have 20 stations on each side, so it's a lot of stations. And compared to the real arrays that we have nowadays. And it's going to have certain difference, certain maximal scale between the maximum distance between the stations. Okay? So this is, so essentially, this was a way to say that when I have an array, what I'm going to get is information about the Fourier components of this image plane, of this two rings structure. And of course, I'm going to get it, but I'm also going to get it with noise and errors that I need to take care of, right? I'm not going to get just the Fourier transform of it. And essentially, these errors, they come in two ways, so they are generally parameterized in two ways. So instead of measuring this, the ideal Vij, I'm going to be measuring something else, Vij hat, in which I have some calibration factors that depends on the two telescopes that I consider. And this essentially is going to encapsulate like physics, local physics that depends on each station, like the elements of the interferometer in each station. Could be also atmospheric turbulence, a series of factors that that we need to take into account. Plus, I will also have thermal noise. Okay, so essentially, this quantity, the quantity I measure, is affected by errors this way. So, in particular, calibration factors. They are relatively, they are complex to measure and complex to determine. So it's so that motivates defining all the variables in which they don't have as much an effect, because you can see that imagine I have a very large calibration factor that I don't know, or it changes very rapidly or very quickly. Then it's going to affect my measure linearly, right? A big change here, it's a big change here, and I don't want that if I don't have these factors under control. Right? So that's what motivates the introduction of closure quantities. Which were originally discussed in these papers in essentially 60s. And essentially, in this case, what we do is instead of having two stations, like I was defining the Fourier transform just by picking two stations before, now we're going to consider a more complicated geometry in the space of stations. I'm going to pick 4 stations, and I'm going to consider, so for each pair of stations, like this one and this one, I have a Fourier transform here, like AJ, imagine that this is IJ, KL, right? So I will have BAJ, here I will have BKL, BJK, so I will have 4 Fourier transform components, right? And I can define this quantity. So I take the logarithm of something that I call closure amplitude, and the closure amplitude is 2, I have 2 Fourier components here, and 2 Fourier components here, okay? So that's the quantity that I define. And when you see this equation, it's like, okay, why is this defined this way? So one quick way of motivating that is that if we go back to these errors, and I don't have thermal noise, you can see like that the calibration factors, when you put them here, they disappear essentially. So you have 4 calibration factors here, 4 calibration factors below, and they cancel. So essentially, in the limit of no thermal noise, this quantity is not affected by calibration factors. So they are robust quantities with respect to that. That's why they were introduced. Because now what happens is, of course, we have thermal noise, and that implies that calibration factors are going to play a role, but the role that they're going to play, it's going to be suppressed because the changes that they introduce is going to be multiplied by the thermal noise. So essentially now I get subliving corrections to these variables. The problem with this is that I make the geometry of the problem more complicated or the data space more complicated, because now I don't have just 2 stations, I have 4 stations. And if I want to plot this, like in the case of the Fourier transform, it was relatively easy to plot because I can plot it as a function of the distance between the stations. But now, if I want to plot this, I naturally have a 5-dimensional space to plot this, because I want to plot closure quantities in a 4-dimensional space, which are my 4 stations that I'm going to be changing, right? And of course, not all the stations, that you can only form a certain set of quadrangles, independent ones, which are given by this. So these are the numbers of independent quadrangles that we can form. And yeah, so this is a problem, which is, it's a higher dimensional data space. That makes it more complicated to extract physics from it, okay, as with any higher dimensional space. So one thing we can do, so we can do a projection of it. We can project it along a certain dimension. In particular, I can say, okay, instead of plotting these closure faces as function of a given quadrangle, and then again, this is like 4-dimensional, it would be a 5-dimensional space interval. I can plot them as function of the quadrangle perimeter. So I'm just choosing a way to project this, right? So it's kind of, in order to be able to have a representation that I can easily see on a screen. And what I get is this. So imagine, and this is now, so all these slides were to show you how the data of these 2 rings, or 1 ring, would look like if you had actual data. Yeah? So this would be your data plot that you would get from your experiment. So this, in this plot here, I plotting 2 things, blue and red. The blue is a 1-ring model, and the red is a 2-ring model. Okay? You can see that for the parameters that I have chosen, there is not much difference. But also, there is the issue is that if we are considering only the 1-ring model, you can see that the data structure is, in this projection, is quite messy. I mean, this is kind of nice. Here, right, we can see some structure. And we know where this is coming from, because I know that these oscillate and they vanish at some point, and this is a logarithm, right? So I expect to have divergences. So I know, like, okay, I can understand that this happens because this one is vanishing, perhaps. You know, like it's kind of like, which is what I expect on the basis of interferometry. Like something is going to vanish, and then what I'm seeing is I see a peak, and that's nice. I see a second peak, but then here, almost like you see, like you have some structure, but it's difficult to really disentangle what's going on. And that's not a problem of the data; it's a problem of the projection that I'm doing in order to visualize the data. And I'm just choosing this visualization, but it's probably not the best one. So what can we do? Or can we do something about this in order to improve or to really isolate the features that I want to see? So we can do something which is, instead of considering all the possible quadrangles that we can form, essentially I look at a subset of the data and see if this subset of the data contains the information that we want. Because of course, like all this information, all these points, they have, with data, they have information about the whole image. Well, every pixel of the image is going to be encoded here in this case, right? But I'm not asking for this question, because if I'm looking for a 1 ring, I don't care about the rest of the image. I'm just looking for a particular feature. So it makes sense that if I can isolate part of the data and find a kind of like physically motivated subset of the data, I may be able to isolate the feature. So we can do something just now at the theoretical level, which is, instead of considering all possible quadrangles, what I do is I fix 3 stations, and then I only modify 1 station. So essentially, I'm just going to be changing the position of one of the stations. And then this way, I choose a subset of the data instead of n to the square independent quadrangles, and just keeping essentially n data points. So this is a way smaller subset of the data. And what happens there is that if I do this, I can isolate these divergences that I was mentioning before. So for instance, I would see this for the 1-ring model and the 2-ring model when I have baselines which are around this value. So essentially, if I take, so this baseline can have different values depending on the station that I choose. Imagine that this was, again, like a very big array with many stations, and I consider like these stations here, like I consider this one, this one, this one, this one, this one, this one. So this is going to be changing the baseline, right? So if I take this station, if I take this to be 3.75 gigalambda, then and I have and I consider stations around this one, this is the plot that I'm going to get. So I'm going to see one divergence with towards positive values, one towards negative values, and I separate the one ring model and the two ring model. And this is happening because of what I was saying before in this function. Essentially, the positive divergence is towards positive values, is coming from one of these quantities vanishing, because then we get the logarithm of something that goes to infinity, and then it goes to infinity. The negative divergences is coming from one of these two vanishing, and then I get the logarithm of 0, so it goes to minus infinity. So that's essentially why I get these structures. Essentially, what I'm doing when fixing 3 of the stations is that I'm fixing 2 of these V's, they are constant, and then all the 2 of them are changing. So this, and then that's why I get 2 types of divergence. So now, this I see one divergence, but this is not enough in order to distinguish between 1 rings and 2 rings. Okay? But if I keep exploring different baselines, I will keep seeing these divergences. And now it's going to be way cleaner than in the previous plot. In fact, what happens is that if I was able to do a plot like this one, a big plot, I will get one divergence here, then another one here, another one here. That's actually what happens when you consider larger baselines. So if you consider baselines around 8.70 gigalambda and 13.6, this is what happens. So then that would imply that if I was able to access this data, so this subset of the data, I would be able to constrain or to know where these divergences are, okay? And in fact, I just need to know these 3 first divergences, so I would have a set of this, like an infinite set of this, in order to be able to distinguish between the 1 ring model and the 2 ring model. So why is that? Because, as I said, these divergences, they come because this function vanishes, and if I had a 1 ring model, in which this is not here, I only have 2 parameters to play with. So these 2 parameters, they are going to completely fix the divergences, the positions of the divergences. So I just need to know 3 positions of 3 divergences in order to be able to falsify this, in order to know if the 1 ring is ever 3. Of course, you can see that the baselines are they are quite large compared to the baselines that we have available now, but that's all the motivation to consider possible extensions of coverage arrays. As I said, at the moment, this is a theoretical stuff. Okay, so this is the content of the talk. So I'm going to summarize it. So if you have any questions before or perhaps I can just jump into the conclusions, which is kind of like it's kind of a summary essentially. So just to motivate, like the physics, when we have physics beyond general relativity, we expect to have additional photon rings, and also we may have different profile for the photon rings, like we can have increased separation between them, increased brightness. So there is a series of effects that we can have. Now the question is, if we want to see this in the data, we have to take into account that the natural variables to consider when dealing with noise and to get rid of them, or to control the noise, or some natural quantities to do that, which are closure quantities. They complicate the extraction of physics, so specific features, just because of the nonlinear nature. So it's a nonlinear definition of Fourier transform components. And the good thing is there is a trade-off. So we improve the situation with respect to the noise, but we lose interpretability, or make interpretations of the data more complex. So that doesn't mean like with any, that's kind of like from this moment onwards, this is a data analysis problem. So it's not, it doesn't imply that we cannot do things. It's an invitation to take a look at the data and see if we can isolate certain features, like slicing the data, which is what I was discussing. And this can be done if we consider quadrangles in which 3 of the stations are kept fixed. And what we can say is that if we want to distinguish for physically motivated models of 1 ring or 2 rings, we need quite large baselines. And this could be additional motivation for space-based stations, for instance. Again, so this was mostly a theoretically inclined study. And of course, this could form the basis for future analysis. So with this, I would like to thank you, and also to thank all my collaborators on this slide. Thank you very much.
Thank you, Raul. And maybe Carlos?
So I will just moderate
So
Tracking constant to the question, what failures or observation did you show in your calculation?
Good one. Yes.
Good, right?
Yes. I
And
should have said that.
okay. And the other thing is, instead of actually dealing with forms, like I understand you want to get rid of dealing with calibration and games, that's why you're using further quantities, but that actually is complicating the calculation. And when you want to fix 3 stations and move just one station, that would actually require a lot of stations to actually get something. Right? Why not actually deal with the games? Why not deal with the
Yeah, actually, so as I said, it's like the motivation is theoretical, but one needs to think about possible implementations for this. And actually, one possibility of in order to have 3 stations fixed and 1 station that is moving is to have a space-based station and 3 stations which are on the surface of the Earth. Then you will have a large baseline, and the variation that you need, you actually don't need to change this station because the rotation of the Earth is going to provide you with an actual variation. So kind of like you can generate a plot like this one, just quite like this wouldn't be like just the distance, but kind of like a time plot. So time will be this axis, and then kind of like because of the rotation, you will have that. And it's like kind of like a very just absolutely. I'm not saying that this is the best implementation, but for sure, like there is always the possibility of dealing with calibration factors. So I think that these alternative approaches.
And maybe other than just dealing with the same frequency, you can just increase the frequency and then you start saying all these speed that was just closer to the
Yeah, but it's like probably you cannot. I mean, like in the next generation HT, there's going to be a frequency of 330, right? Hertz. 345. Okay, yes. So it doesn't give you. I mean, it gives you a factor of 1 point something, right? So it's not going to be such a big effect. So perhaps because I mean, what I mean is that you are limited by how higher the frequency you can go.
Yeah.
Yeah, it's a.
Sorry, I may have missed this, but let's say that you are actually observing a real model, and you look at the low pressure amplitudes, the data that you observe. How would you distinguish between a one-real model and a two-real model? Based on the position of the divergence of the so
essentially you would need to be able to. Well, I mean, like one possibility would be here. And I imagine something that you could do is to, because I mean, this is the actual difference like, between, of course, not with as many data points as here, so you can imagine you would have less data points, and this actually, you can ask whether or not you can see the difference between these two. So I think in general, with sparse data points in this kind of plot, we're not going to be able to see it. Right? So that's the motivation to consider this slicings. And if you do this slicings, the idea is that you can isolate these divergences. Then you will need to isolate 3 of them in order to classify them. Essentially, because these divergences, you can see them as they are just telling you the locations of the zeros of your function, right? And the zeros are controlled by the parameters of your model. If your model has only 1 ring, you only have 2 parameters. Right? With 2 parameters, you fix all the zeros. So you fix all of them. So you just need 3 zeros in order to be able to say, because the 2 first ones, you can always adjust by choosing the parameters of your model, right? So you have 2 parameters, the first 2 positions, you can change them. The third one is fixed. And you can really falsify your model by going to 3 variables. So that's essentially what you need. You need to be able to, that's why you need large enough baseline in order to be able to see, to go far enough to see this. Does it answer your question? Yeah.
Thank you very much for this talk. Perhaps this is a crazy question. I am wondering if you plan to apply this Turing model to detect the rings, for instance, in the black hole of our galaxy or in a bad galaxy. These are the plans, no? These are the targets that I don't see this.
So I mean, ideally, that would be the idea. So the thing is that with the data that we have right now, because we don't have these baselines essentially available, we're not going to be able to see. So if you can conclude is that unless you have baselines of this this size, then you're not going to be able to use this method in order to reach 100. Then in the future, it could be something to keep in mind, so that when we consider extensions, and this kind of like, that's also part of the motivation of this study, it's also a very good study, but also to see when we consider extensions of the next generation of Python threshold, like which things are more or less interesting from other. And then you think about, so one thing is the theoretical study, and then you see all your theoretical possibilities, which you see which things are feasible or not from a practical perspective. So I think more about this, it's kind of like extensions to the future, kind of like studies to it, and we can do it.
Well, and what about with the black hole rotating? But I'm not an expert in this, but I have heard that with black hole rotating, you see a region, not a sphere of photon. So I guess that the Turing model has 5 ways. Yes, you want to do it.
Eventually, we have to do it. So I mean, it's going to be more complex this Turing model. So in the sense that it's like generally what is going to happen with rotation is that if it's difficult to see the difference here in spherical symmetry, like the more parameters and the more physics you introduce, the more difficult it's going to be to time or different effects. Right? So that's why we started for this, because it's like a very optimistic simple to analyze also one, but it's also like the most optimistic situation. Now as you of course you have to do rotation, you have to include uncertainties, and you have to equation this physics, you have to take all this into account, and then you have to see how to use in time all these things. That's an activity. That needs to be but it's like kind of the start from
Yes, beyond, for instance, imaging and the limitations that you show us about the Turing models to be like actually distinguished with the data that we can get, for instance, in the next, let's say, X years. Are there any other features that we can search for? Like, for instance, this whole thing arises from considering a pure reflection object in the middle. Doesn't that provide an additional source of energy and heating to other components, such as, for instance, like the ISO? So we can expect to see like a change in the temperature or another different profiles that can also complement information in the meanwhile. How can we search for that?
Yeah, good question. So that's certainly something that could happen that hasn't been analyzed, or also the model I was discussing. The question is not changed, or physics is happening in the same time. Ideally, of course, you want to do a model in which the things are coupled. So if you change the nature of a certain object, also do this, so the properties can change, right? That's something that hasn't been analyzed. But also with this model, as you said, I was focusing only on reflection. But if you have emission, then what will happen is that essentially you will have some brightness in the center. Essentially, that's something also that you can test. Right? Essentially, it's the dynamic range. The higher the dynamic range that you have, the more constraints you can place on the emission. So it could be additional things. But I just thought about the example of reflection would be more interesting. That's something additional. So it's again, so you have. Also the thing is that reflection is cleaner because you have less uncertainties. If you consider emission, again, we have all these issues of you need to know the spectrum of emission, and you have additional model in the time scales. But eventually, it's something that needs to be analyzed. So I know that I want you to model it.
No, that's perfect.
I started moderating myself.
So, is there any additional question? I understand that you are interested in seeing if you can handle this in the linear domain. You could also try making an image of the data that you have to make and see if you can actually extend the image. There's no problem.
Yeah, but I'm not sure if the uncertainties that we introduce also in the image reconstruction procedure is going to be make the procedure really comparable. I mean, I don't really know how to compare that, because you always introduce some experts. But it's true, you can also do that. Let's see which procedure is optimal.
So, one last question, or well, if not, those things.
Thank you.